Hello, YouTube. Today we're going to talk about linearization. This one's probably going to be a minute, and it's kind of a concept where honestly it's pretty weird. And once it clicks, it should be fine, but until it clicks, it's going to be really hard to tell why you're even beginning to care about any of this. So the big one is that hopefully you should be able to use graphical modeling to basically figure stuff out about a situation by hand. Ideally, perfect world, you're able to recognize graph shapes a little bit, and then you're able to take your data and realize how you're supposed to linearize it. A lot of that will just be play around with it, see if it works. And then using the slope intercept of linearized data in order to find values that you're looking for. Um, so if we've got some, uh, let's say we've got some graphs, and um, the first one we've got here would be a line, nice and easy. That tends to follow the equation form y equals mx plus b. And that I want to stress about this, and I just realized I'm going to have to move my face. Something that I want to stress about this is that the x in this case is representing whatever you graph on your x-axis. The y in this case is representing whatever you graph on your y-axis. M would be the slope of this line, B would be the intercept of this line. Hopefully that's something that you're somewhat familiar with. Something that's really important about that is that M and B can both be visually identified and figured out by a person looking at this graph. If I compare this to this one, where it's y equals kx, where k is a constant and x is some changing value, squared plus b. B is still our y-intercept, so that part's easily identifiable. That's nice. I don't know how to look at a curve and tell what k is, personally anyway. X is still the whatever's on the x-axis, y is still whatever's on the y-axis. So as long as you have a thing that you're graphing on the x-axis and a thing that you're graphing on the y-axis, if the graph looks like this, it means that the equation underlying the graph is of that form. If your graph looks like this is typically what you'll get when you have something along the lines of y equals k over x, and this is something that you'll have when you have something along the lines of y equals k minus a second constant divided by x. Which is, so these are sort of the three shapes that are likely to come up. There could technically be other shapes, absolutely. Actually, one that I don't have on here, which could definitely come up, is one that follows the equation for gravity. So force of gravity is equal to a whole bunch of stuff divided by distance squared. And the inverse squared relationship is one that does actually come up fairly often. So what our goal today is that because if we see a line, we can use and figure out the underlying equation that governs that graph really easily. If I see a parabola, I can tell you that it's based on x squared, but I can't tell you what k is. So I can tell you a little bit about the equation that underlies it, but I can't literally write out the equation that makes up that graph. Our goal today is to take it and make it so that we change the way we're representing our data, not so that we've changed our data, but so that our graphs have a different shape and our graphs look like lines. That's the goal. We're turning them into lines, aka linearization. So when you have a graph that's y equals mx plus b, it is much easier to analyze. The y-intercept of that graph will be the b. The slope of that graph will be the thing. if we have an equation like 1 over the mass times the force applied plus the force of friction is equal to acceleration, we really want to change this graph so that it will become a line, so that we can actually look at the plot, look at our graph, and have it work. And the core idea or the core premise here, we'll come back to that other one. The core idea or the core premise here is that if you graph different data, or if you manipulate your data before you graph it, then the graph will look different. So for example, say we start out with some data, and our data is from the equation x is equal to 5t squared. Now let's say I don't know that that's my equation, but I do know that the graph looks like this. If I try to fit a line to it, that line does not work because that's not the shape of this graph. If I were to take the time and I were to double all of the times and then graph it, the graph would look much more spread out. If I were to take the times and I were to cut all the times in half, so for every value, I just graphed what it would look like if I had cut the time in half. Oof, I don't know why I'm so yawny right now. Then the graph would look something like 4 would become 2, so we're here. 5 would become 2.5, so we're here. The graph would look something like this, where we've got the same basic shape of the graph, but it's more smushed in. So what's happening there is I'm literally just changing. I'm doing a set thing to all the data before I graph it. As long as you're careful about it, and as long as you label your axes correctly, this won't change what the data is per se, but it will change what your graph is showing. And so in this specific case, if I take my time and I don't graph time, but instead I graph time squared, here's what happens. So if I take all of my times from the previous data table, so in this case we've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we square all of those. So instead of 0, we'll have 0 still, because 0 squared is 0. Instead of 1, we'll have 1, because 1 squared is 1. Instead of 2, we'll have 4, because 2 squared is 4. 3 becomes 9, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, 10 squared. Now, if I graph time squared, I'm effectively treating all of this in my equation as if it is one variable, the variable on the x-axis. And when I do that, I suddenly get a line. That line is something that I can interpret the data from in order to actually answer things about the sort of graph that makes it. We'll come back to these couple examples, but broadly speaking, that's your goal. That's what you're shooting for. Let's go into how we actually do it. And as this says, it's way too much to type. It's a pretty complicated concept, so I'm just going to sort of write out the steps on a sheet of paper, and we'll go from there. Okay, so when you're linearizing, there are a couple different ways that it can wind up going down, and if you have the equation available versus if you don't, are going to be pretty different. I'm going to focus on what happens if you know what the equation is supposed to be, because that one will typically be what you're asked to do. But technically what you can do is you can actually change the axes that you're graphing, and when they become a line, that will tell you what equation form you're actually working with, which can be really helpful for figuring out what type of equation it is. Again, that one doesn't show up as often. So the goal here is to start with an equation. So let's take that one that we just had. X equals 5t squared. Now that's not a line. What I want to do is replace things to turn it into a line, and then make my graph reflect the things that I've replaced. So the first thing I'm going to do is identify what I want to put on my x-axis and what variables I have data for. The variables I have data for in this case are x and t. And I've got numbers. The problem is when I graph those, it's not a line. Instead, it looks like a parabola. And if I look at the underlying equation, that makes sense because this is the equation for a parabola. When I'm graphing it like that, if I just graph this as my y-axis and this as my x-axis, what I've done is I've actually kind of effectively replaced the x by saying, all right, well, this is the y-axis. I've got this 5 hanging around. The t is my x-axis, and that'll get squared and then multiplied by 5, and that should give me basically whatever my y is. If I take the thing I have on my x-axis and I square it, multiply by 5, that gives me my y-axis. That's what this equation says. What I want to do instead is find a way to represent it so that it'll look like a line. The reason this doesn't look like a line is because this squared is in the way, so I need to get rid of the squared. So instead of making my x-axis be t, which when it gets squared stops it from being a line, if I make my x-axis t squared, then what I can do is instead of just replacing the t by saying the t is what's my x-axis is t squared. And when I do that, my y-axis will be x. 5 will be multiplied by my x-axis. If I look at this is suddenly starting to look a lot more like a line, especially if I recognize that the thing in front of my x-axis is going to be m, or the slope. So our goal in this is to look at the equation, once we've looked at the equation, figure out what you need to replace with y's and x's so that you'll be left with y equals mx plus b. In this case, our plus b is plus 0. So 0 would be our intercept. In particular, when you're replacing for the y-axis and the x-axis, make sure it's stuff you've measured. If you are having to, so like in this case, when I'm looking at it, I'm like, okay, well, t squared needs to be replaced with the x-axis so I can get rid of that squared. My next step is to do the things that like I'm replacing with the x-axis to my data. Then you want to graph the new altered data, and if you did it right, you'll get a line. And then once you've done that, you can analyze that line to figure out whatever you were actually looking for. So I think that this process again tends to be pretty weird and fairly counterintuitive for people. My plan is to just do it a couple times, and a couple times out of the context of the AP exam, a couple times, and then once in the context of like an old AP exam question, so you can see exactly what you would be expected to do. All right. So taking another example, if I look at some data, I've got M and I've got A, and when I look at my data, it's not aligned, so it's really hard to analyze. If I look at the underlying equation, my data that I have available is A and M. So I'm going to want to take this, and I'm going to want to find a way to replace this with stuff that I can actually have be aligned when it's done. If I look at my two things that I have measured, I've measured A, that's not a good choice of color, and I've measured M. When I look at the equation, the reason it's not a line is yes, something equals whatever is my y-axis, so this is just my y-axis and that's fine. But I'm not graphing the thing as my x-axis, I'm graphing 1 divided by the thing that I've put as my x-axis. So what I want to do instead is sort of take this whole thing that's being done to M, and that will be the thing I need to put on my x-axis. That'll be the thing that I need to do to my data. So to do that, I need to do 1 divided by M. And when I take the M's that I had previously had, which if you look were 0.1, 0.15, 0.2, 0.25, 0.3, if I do 1 divided by those things, we get 10, we get 6.6, we get 5, we get 4, we get 3.33. And when I graph those pieces of data, now it looks like a line. And the reason why that's happening is because if I look at this equation and I replace the 1 over m, which is a variable, with the variable x, because this is my x-axis, and I take the variable a, the thing that's changing in these equations, and I replace it with the variable y to represent that it's my y-axis, what I'll have left over is a constant, which is going to stay the same the whole time and be the slope because it's the thing in front of the x, plus some other constants, and I will once again need to get my face out of the way, plus some other constants, and those other constants in this case are my intercept. Hopefully this is making some level of sense so far. Again, it's going to be really weird until it clicks, and then once it clicks, it should hopefully be fine. Once you then have your graph to look like a line, the next set of steps is to compare those two equations sort of side by side. And if I compare this, the stuff that's being multiplied by x, that's my slope. The stuff that's being added to x, that's my intercept. So what you can then do is, because I said is, right? Is means equals in math terms. So what I can say is that if I look at my graph and I calculate out my slope from my graph, that will equal the force of the fan. So whatever the slope is, that'll be the force of the fan, and that one's pretty straightforward. For the intercept one, that's a little more complicated. What I would be saying is, whatever my intercept is, that's equal to mu, that would be mg. No, it would be mu g. Right, that's why it's 1 over m. Sorry, I'm using actual equations, and while, again, this is unit 0, so the physics of it won't necessarily click, it does still exist, so I want to make sure I'm not messing it up. So what I could then do is if I had the intercept, I could use that to solve for either mu if I knew g, or g if I knew mu. You will probably know g, not mu, so I would use it to solve for that. So taking a sec to do it with these two examples. If I look at my equation, the equation that this is actually supposed to be is x equals 1 half g t squared. I need to take my t squared and replace it with x, because that's my x-axis that gave me a line. I need to take my x and replace it with y, because that's the y-axis that gave me a line. When I do that, I'll have y equals some stuff times my x-axis. The some stuff is my slope of this line. So what that does is it tells me that when I look at my solved equation and it's 5 times x, that 5 is my slope. But my slope also equals 1 half g. So I could set that equal to 5 and solve the equation that made by looking at my graph to get the slope to figure out what g is. And that's the thing that's really useful about this, is that a lot of times questions will be like, here's this data. Based on the data, what's g? And that would be a question that they're asking where you would actually be expected to linearize and use that linearized data to figure out g. And the reason why this is so important, and one of the biggest things that people tend to run into problems with, is they're just like, well, can't I just pick 2 data points? Like if I calculate it with 21 and 4, I can just calculate g. The problem with that approach is it's only using one measurement from one data point that you did once. And as we talked about a little bit with the experimental design stuff, you really don't want to do that because it means it's susceptible to any problems that happened with that one, which might not have happened with others. The nice thing about linearization is that by fitting a line to all of your data, you're using all of your data to come up with an answer. So this is a way of reducing experimental uncertainty by fitting a curve to a large sweep of data to use all of the data at once instead of using just one data point. And that's why we're bothering with any of this, actually. So solving this out, I could multiply each side by 2, multiply each side by 2, and that would tell me that g is equal to 10. In this case, my intercept should be 0, and if you look, it is pretty close to 0, so hopefully here the intercept is just 0. All right. Next one. So let's take that equation that we just dealt with a second ago. If I'm looking at this, I need to replace this with x. I need to replace this with y, because those are the things that I can graph that will give me a line. Once I've done that, what I'll be left with is that y is equal to the force from the fan times x minus mu, whatever that is, times g. If I look at my graph and I find an equation for it, whatever's in front of x will be the slope, but will also be the force from the fan. So the slope in this case will be equal from the force from the fan because that's the thing that's in front of x in the equation. And in this case, that's 2. So I just have the force from the fan. Nothing needed. The intercept will be equal to minus mu times g. So if and that in this case is minus 6. If you know that g on Earth tends to be very close to 10, we could then solve this out by dividing each side by the 10, and that would let us figure out, or negative 10, and that would let us figure out that mu in this case is 0.6. So this would be useful for saying, based on this experimental data and using all of the data, what's mu, what's the force of the fan? And this, a lot of times they'll come up in like multiple choice questions where it's more along the lines of like, what does the intercept represent? And being able to linearize is a sort of long way to get to that answer, but also kind of the only way to get to that answer. Although you would just have to stop. You would basically just look at the equation form and be like, oh, this is what the intercept is. And you'd be good to go. Okay, so I'm going to go to a publicly released College Board question now and do that question as sort of another example of this process. You can see the way it looks in an actual like problem and why I'm doing all of this stuff and like what you would be expected to do. So we're given a bunch of data. A group of students prepare a large batch of conductive dough, soft substance that can conduct electricity, and then mold the dough into several cylinders with various cross-sectional areas A and lengths L. Okay, so A is the area of the dough, L is the length of the dough. Each student applies a potential difference, delta V, so delta V is the amount of potential that there is across the ends of the dough cylinder, and determines the resistance R of that cylinder. The results of their experiment are shown in the table below. So we've got 4 variables that we have to work with. Something that's really important, we don't have to use all of them. These are the things we can use. The students want to determine the resistivity of the dough cylinder. So what this tells me is that resistivity is the thing that absolutely 100% must show up in whatever equation I'm trying to use, because that's the thing I'm trying to find. Indicate below which quantities could be graphed to determine the value of resistivity of the dough cylinders. You may use the remaining columns in the table above as needed to record any quantities that are not already in the table. So what I'm going to do is go to the AP Physics 1 equation sheet, and I'm going to look for something that has resistivity, and I'm also going to look for equations with resistivity, and ideally it should hopefully also have other stuff that we already know. So looking at that equation sheet, I don't see anything for resistivity over here. Resistance, that's close, but that's not resistivity. Oh, resistivity. So rho is resistivity. Does one of these equations have rho? Doesn't have rho, doesn't have rho. Oop, this one's got rho, so this one I might use. Doesn't have rho, doesn't have rho, doesn't have rho, doesn't have rho. So this is the literal only equation that has resistivity in it. So that's the equation I'm going to take back with me to the problem. Capital R is equal to rho lowercase l over A. Capital R is equal to rho lowercase l over A. If I look at this equation, I want to figure out what the resistivity is. If I graph the stuff from the equation, though, I'm not going to get a line, because this doesn't look like y equals mx plus b. But if I'm looking at this, this is all by itself on the left. I'm actually just going to go ahead and call this my y-axis. So my vertical axis is r. My other things that are changing, that are variables in this case, are L and A. So I'm going to go ahead and make those two my x-axis. So if I take L over A and I make it my x-axis, then suddenly what I'm left with is my y-axis. Let me rewrite that some more cleaner. My y-axis is equal to rho times my x-axis. This is a line, because it's just a constant value, the resistivity of the dough, times a variable, in this case L over A, and that'll equal another variable, my y-axis, R. So I need to redo part of this table with L over A. So taking a calculator, I'm going to literally manually punch in and calculate 0.03 divided by 0.12349. That's my L over A for this one, and it's 61. For the next one, we've got 0.05, and that's being divided by the same thing. It's 102. And I should technically round that to 100, because there's 2 sig figs on all of these, but whatever. We've got 0.08 divided by 0.00053. So that's 151. And last up, we've got 0.015 and 57, which gives us 26. So this is going to be my y-axis when I graph. This is going to be my x-axis when I graph. So now, actually graphing it, I want to make it so that my scale is such that the whole thing gets used as much as possible. My biggest number is 150. Basically, my smallest number is 20 some odd. I do want to put 0 at the beginning for both of these. My x-axis is r, which it tells me as units of row. Ohms. My x-axis is L over A. L has units of meters. A has units of meters squared. So we've got meters divided by meters squared, so that's 1 over meters, because one of the meters from the top cancels with one of the meters from the bottom. So we've got L over A as our x-axis, and that is 1 over m for my units. If each of these boxes is worth 5, that gets me to 25, 50, 75, 100, and that'll be high enough to reach up to the 105 that I need to. So 25, 50, 75, 100, 125. I see no reason not to just do the same thing for L over A. I guess I need to go higher, so 25, 50, 75, 100. That'll just barely let me get up to 150, and 150, 151 is going to round to pretty much the same thing, so that seems fine. 125, 150. And from there, all we got to do is throw some dots at it. So our first dot is going to be 61, 23.6. So 60 is here. No, it's not. It's here. 61, 23.6, which is here-ish. 102 and 31. So 30, 102. 151, 61. I feel like I did this calculation. Oh, yeah. Hold up. This should have been 150, not 015. So this is actually 200 and... I need to change all my axes. That's annoying. This is 263. So I'm actually going to make this one be 50. I'm going to make this one be 75. I'm going to... this one be 100. This one be 150. This one be 200. This one be 250. This one be 300. And then that'll actually make it work. And I'm going to have to redo my dots. So 61, 23, 23. Each of these is 10. So this is 61. 102 and 31. 102 and 31. 151 and 61. 50, 55, 60. And 105 and 263. So that should be up here at 105. Great. So if I take a straight edge, which will just be another sheet of paper in this case, and try to draw it so it roughly goes through those points. And if I'm being careful about it, the equation should go through 0, 0. You don't have to force that. In this case, I'm going to get kind of close to forcing it. That'll be my line of best fit. And by using my line of best fit, that'll make sure that I'm trying at least to use all of my data. If I take my new equation, I've got that whatever's on my y-axis equals my resistivity, the thing I'm looking for, times my y-axis, x-axis. The constant being multiplied by the x-axis is your slope. So my slope for this one will equal my resistivity. Calculating my slope out, it crosses a corner here, it crosses a corner here, so this is up by 25 over by 10, 20, 30, 40, 50, 60. So my slope here equals rise, 25 ohms, over run, 1, 2, 60. Which means that my resistivity is going to be 0.42 ohm meters. And that's how you linearize. There is more to the question, but I don't think it has to do with linearization. Let me double check that. Yeah. Yeah. So the basic premise is, again, what we're doing is we're taking an equation that's not a line. We're figuring out what's happening to our variables to make it not be a line. And we're doing that thing to our variables in advance. By doing that, if we graph that thing that's happening to our variables instead of the variables themselves, just by themselves, we'll suddenly get a line when we graph it. We can then use that line to use all of our data to figure out values like slope and use that to get actual information from our data using, again, all of our data instead of just a subset. So that's it. Again, really weird concept. This one especially, if you can find a way to like work with someone on a problem involving linearization and then who knows what they're doing and sort of get help from them as you go through it, that's probably going to be the best way to do it. But hopefully this was able to help a little bit. Goodbye, YouTube.